by Eliezer Rabinovici. Okay.
Okay, so I knew Robert, I met him twice actually, which I remember vividly. I remember him as a very modest, low-speaking person. I met him once when he got the EPS prize in 1996 in Jerusalem, in 1997 in Jerusalem, and then when he got the Wolf Prize at the Knesset. I was very much impressed not only by his work, but by his personality. My talk, I changed slightly the title. It will be about 3 stories of spontaneous symmetry breaking. I must say that I hate Skype talks, and I'm really sorry that I have to do that. So the outline of the talk is I will first discuss spontaneous symmetry breaking of some space symmetries, and I'll put them in the context of solid state physics and in the context of particle physics. I will discuss some consequences of conformal and scale invariance and their breaking, and then I will discuss some new results on and old results on the phases of gate theories and gravity. So I will start with spontaneous symmetry breaking of space symmetries. Now, one usually considers internal symmetries and their manifestations, and the Brout-Englert-Higgs mechanism is one such case. But I want now to consider a different phenomena, a phenomena in which, for example, a liquid turns into a crystal. This solidification and crystallization involves the breakdown of a space symmetry. Now let me remind ourselves, in general, the ground state wave functional is found by considering first all wave functionals which have the same expectation value of the field operator phi. Next, one finds the lowest expectation value of the Hamiltonian in that class of wave functionals, and one picks this candidate out. And finally, one looks at the effective potential, which is the minimum over all these expectation values phi twiddle, and from there one chooses who is going to be actually the wave functional. So finally one finds the wave functional corresponding to the lowest of all these minima. So one draws some complicated potential. Next, one finds the wave functional of the ground state. Now usually we don't look at the full complications, but one identifies what is the wave function. Now in the process of identifying it, one usually assumes that the ground state will be found among those wave functionals which give an expectation value to the operator phi twiddle, such that phi twiddle does not depend on space-time's coordinates. And I, for example, wonder to what extent this was ever proven in the standard model. But it's clear that we always assume in our calculations and in what we teach our students is that this wave functional will be found, the ground state wave functional will be found among those which gives a constant in space expectation value. Now, I'm going to follow here the work of Lev Landau, actually, in 1937, in which one does not make the above assumption. Now, in order to be able to obtain that the ground state wave functional is such that the expectation value in the ground state of the operator phi is a phi twiddle, which is space dependent, this requires several ingredients. So first, consider a scalar Landau order parameter. It's Landau's paper, so he defines his order parameter. And this order parameter, rho of Q, monitors the transition between a liquid and a solid. So let us write first in X space. So rho of X is the density of the solid, which should be X dependent. minus the density of the liquid, which is constant. Now one writes the order parameter in a Fourier expansion, so one then highlights the possibility of having some component of the wave functional having support also for non-vanishing values of rho of Q. So what is needed for that? So the first term that Landau wrote in his action, the quadratic term, is the most general term. I've written it here for 3 spatial dimensions. The most general term is one which obeys rotational and translational invariance. So it contains a delta function of the vectors Q1 plus Q2, which ensures that indeed the translational and rotational invariance is observed. Now, notice what we don't usually think about. There is this A of Q1 squared, and it's now Q1 and not Q1 and Q2 and all the scalars you can form because of the delta function. And in general, this function A of Q squared in this Landau action should be determined by the microscopic theorem. Now, what is the shape of A of Q squared? So for what we are used to, for a field theory describing a massive particle of momentum Q, one simply has that A of Q squared is Q squared plus M squared. That's what would be for a relativistic field theory. In that case, if we draw A of Q squared as a function of Q, absolute value, it is clear that the minimum is obtained for Q equals 0. That is, indeed, the vacuum for a free relativistic massive particle does not break down translational invariance. It obtains the minimum for Q equal 0. So we don't have any breakdown here of space-time symmetry for a free field theory. However, what would happen if the microscopic theory would lead to an A of Q squared, which has the following form? Namely, it has a minimum, but not at Q equals 0, but at some value Q naught. In that case, we know that the vacuum would have support on a sphere in Q space whose radius is not 0, and it is some value of Q naught. So one has actually, in such a situation, broken I'm sorry, I have to answer the phone, and I apologize for this. Amir and Ben Zatzan, Jochen Schau. Is it the hoof? Okay, but okay, I apologize for that. Okay, so this happens, for example, in the case of a neutron star, as was shown in 71 by Bain, Bethe, and Pettit. In that situation, when you look at the repulsion and attraction of the various components of the ingredients of a neutron star, you get such, from the microscopic theory, you get this macroscopic function of A of Q squared. So what are the consequences of that? Well, as I said, translational invariance is broken. But as we know, a solid also obeys, also disobeys rotational invariance. So how do we obtain that? For this, we need to go to the next term in the Landau-Ginzburg-Lagrangian. So that term will be now an integral of Q1, Q2, and Q3. It will have some macroscopic function B, which will be a function of all the invariants. Again, it must be translationally and rotationally invariant in the Lagrangian. So one has a delta function of Q1 plus Q2 plus Q3. Now, what does that mean? If you take Q1 and plus Q2 plus Q3 to be equal 0, you are forming, in general, a triangle. Now, the next step is, assume, for no good reason, but it's 1937, assume that this expansion is exact in some limit, so the approximation makes sense. In that case, let us use the fact that the vectors Q1, Q2, and Q3 are all sitting on the sphere. That is, all of them have the same length. So this implies that we now need to triangulate the sphere, and we need to take out triplets of Q1s plus Q2 plus Q3. However, notice that at this stage, Q1, Q2, and Q3 are of equal lengths in this approximation. So this determines that one has an equilateral triangle. So out of very simple considerations, I think rather dramatically simple, one obtained that the Q's, in case one has an A of Q squared, which gives a non-trivial minimum at some value of Q naught, is indeed an equilateral triangle. Now, because rho is real, actually for every Q1 you need a minus Q1, so actually it's not only you commit to one triangle, but you always have a triangle and the other triangle which will ensure that the density is real. So then one has to begin to consider the fact that not only translational invariance was broken, but rotational invariance was broken. And while translational invariance was broken in a general way, which depends on the dynamics, so there is no a priori statement on what Q naught is, the rotational invariance is broken in a very precise way. You obtain a concrete angle of 60 degrees. So now one has to do the general consideration, and one finds that actually the ground state, one finds that when you do this triangulation, there is only a finite number which could lead to the maximum. The moment you have too many of those, the contribution is not a competitor for being the ground state. So you need for every dimension, here's 3 space for example, to try and take all those triplets with 60 degrees and see where you obtain the ground state. And in the case of 3 dimensions, this is actually what one obtains. This is rho of x, y, and z. This configuration is going to give the minimum for the minimum energy and the best possible value for the Lagrangian. And this is the value which you see. Remember, B was the value of that macroscopic object, which is unknown. You have rho of Q naught, and this is the winning configuration. And in real space, this is a BCC, a body-centered cubic lattice. So as you saw, out of very simple considerations, you have a very strong prediction. All crystals must be of the BCC type. Well, that's a little bit too strong, because first of all, I don't know if Landau knew it at the time, but the transition is first order and not second order. So this whole idea of doing work this way is only valid near the solidification point, very near to it. And actually, you find that when one looks near the solidification points, on the left side of the table of elements, you find that 40 metals form BCC lattice near that point. This was shown by Alexander Matei. There are some details have been challenged things, but I think basically the result that experimentally and theoretically one has a large amount of BCC lattices is really very impressive example of the power of the analysis of spontaneous symmetry breaking. Now, what would have happened if the third order term would have been absent, which is usually what happens many times in our case? So what would happen if we had a fourth order term? Well, I can't see you, the audience, so I can't ask you to think a moment about it. But I think it's clear that the moment you would have a delta function of Q1 plus Q2 plus Q3 plus Q4 being the first determining term after the quadratic one, you realize that the angle is ill-determined because a rhombus can have any possible angle. So in that case, it's really crucial in order to break rotational invariance to have the third order term. What does this have to do with particle physics? Well, one issue which bothers, I think, I know that bothered Francois for many years, was the issue of what about dynamical compactification? We usually assume some compactification, but actually we shouldn't be content having that, and there are two ways to look at it. One is that somehow 10-dimensional space is there, and it's then spontaneously broken down to the world of 4 plus 6, or that we have a cosmological model, and somehow 6 dimensions don't ever expand appropriately. So if we take now the point of view of trying to see how compactification can occur as a spontaneous symmetry breaking, I would say that in particle physics there is one person, the bad guy, the tachyon of string theory, which actually obeys all the ingredients that you need. In order to make it a dimension 1-1 operator, it needs to have a non-zero momentum, and it definitely has 3-point interactions. So at the time with Eliezer and Forge, we thought that this could be a way to implement the compactification in a dynamical fashion, and actually almost worked in the sense that the tachyon could form the type of SU2 lattice or an interesting type of equilateral triangle, and on top of it, by taking the energy density from the theta mu nu term, namely d mu t, d mu t, you would get some constant so that r mu nu would have to react by curving. So this was actually, we were very happy with that result, but then we realized that as topology changes involved, maybe you go from flat space to a sphere, this approximation is unreliable, and you can't take the plane waves with a finite number and try to approximate a sphere, and this is where we got stuck. So this was story number 1, almost. So where, nevertheless, can we think of compactifications coming from solid-state systems in another way? So the ideal system is a liquid crystal. Liquid crystals have an order parameter which is very conveniently a symmetric tensor, and it breaks down translational and rotational invariance only in some directions and not in others. Again, something which is very similar to what we dream about when we talk about compactifications. Unfortunately, no more programs in that direction. I didn't mention at all the issue of the breakdown of time translational invariance. I will just say that one way you can think about it is consider, for example, conformal quantum mechanics, where the potential is a lambda over x squared. In that case, the spectrum of the system is bounded from below, but you don't have a ground state. This is, in a way, a direction in which you can have a breakdown of time translational invariance. I will stop here on the issue, the very exciting issues of breaking of space and time translation invariance, and attached to conformal quantum mechanics, I want to discuss a second story, which is related to the conformal symmetry or scale invariance. I'm not, Yaron, I'm not here arguing between the two, and I want to relate it to the vacuum energy. For that purpose, let us remember another Russian scientist, Zeldovich, who actually, one could, in his language, paraphrase the following problem. Consider QED in the 40s. It has a proton, an electron, and a photon. We believe we understand physics up to a Rydberg scale. So we could write down an effective field theory, which is valid up to the Rydberg scale, and we would conclude that the value of the cosmological constant should be at least a Rydberg to the 4th. This suggesting a very serious problem. But there is a loophole in this argument, which is now haunting us for many years. We know already from the work of Weinberg and others about low energy effective theories where symmetries have been spontaneously broken, that when you write down the effective low energy theories, you need to include all symmetries, be they either explicitly or spontaneously broken. At the moment you do not constrain your effective low energy theory by the fact that you have symmetries, then you are at your own risk. If you would write down the chiral Lagrangian, forgetting that you have spontaneously broken chiral symmetry, there would be no way to try and do the famous low energy theorem, so try to get the mass of the row. This would have totally failed. Now this is also true if the underlying theory of nature has no scale. And I want now to ignore the fact that the cosmological constant is very small. I still want it to be zero. I have the great advantage that I can't see the crowd, so I can't see a reaction to that. Now, the claim is that if the underlying theory of nature has no scale, and by the way, this would include string theory. I imagine alpha prime is some scale spontaneously generated. Then the claim is that the vacuum energy of such a theory does not depend on the scale of spontaneous symmetry breaking of scale or conformal invariance at all. It doesn't matter, the vacuum energy is the same if the theory has a breaking of scale invariance or not. So this scale, which you could have assumed is your cutoff scale, is not relevant for determining the vacuum energy. And this we should remember. Okay, here is an example. So consider a three-dimensional theory, which is the large N vector model with an interaction with a marginal operator in 3 dimensions, which is phi to the 6. So take phi squared cubed and go to the limit where n goes to infinity. And take the limit n goes to infinity for a fixed UV cutoff lambda, and only then take the cutoff to infinity. In that case, the beta function of the theory is 0. 1 over n corrections break conformality. If you would take the opposite order, the results would have been different. Now, write down the effective potential of such a theory. So go to sigma, which is an ON invariant, which would be the Lagrange multiplier, which would be phi squared. And let's consider what would be the most general possible effective potential as a function of sigma. So the theory having a 0 beta function, it has no scale. So the effective potential would be, the scale of the potential would be determined by the scale of the field sigma, so it would be sigma cubed. And this would be multiplied by some general function of G6. Now, in the model at hand, there is a specific value for that function. But let's do a general analysis, independent of what that function is for a moment. So here on a table, you see the function of G6, the expectation value of sigma. The question is, there is a spontaneous symmetry breaking or not, or if there is scale invariance. What are the masses in the problem, and what is the vacuum energy? So let us first consider the case where G of 6 is such that f of G6 is positive. In that case, the expectation value of sigma at the vacuum would be 0. There would be no breaking of scale invariance. All masses in the problem would be 0, and the vacuum energy vanishes. What about the case when G6 is such that f of G6 is negative? Well, in that case, actually, the expectation value of sigma looks to be something like infinity had there been a vacuum. The theory in any case is ill-defined, and if we would put a cutoff, we would have masses of the order of the cutoff, so it's not a theory which can be there's no low energy theory there, and the vacuum energy, which is ill-defined, is minus infinity. I should say that there were attempts to use these in some holographic dualities, but this theory is ill-defined. Let's go now to the case where f of G6 vanishes. Well, in that case, we actually have two possibilities. The moment the potential vanishes, you will see that the expectation value of sigma could be either 0 or not 0. Scale invariance would be broken if you chose it, if you chose the expectation value to be non-zero, and it would not be broken if you chose it to be zero. If it's not broken, you are back to the case where f of G6 was positive. You have mass is zero and vacuum energy zero. On the other hand, you have a massless dilaton, but you have massive particles, let's call them pions here, and let's call the dilaton, okay, there is a massless dilaton, and there is the other equal mass, non-zero mass particles. But the vacuum energy remains all the time and is zero. So the vacuum energy doesn't care if you have introduced the scale sigma or you have not introduced the scale sigma. And this is the loophole in the argument of Zelidovich. Now, you could have been tempted, again, to say, well, there are particles of a certain mass. We know the physics till that mass. Let's write an effective field theory, and then the energy of that effective field theory will introduce a vacuum energy, which is of the order of the expectation value of sigma cubed. But that's wrong. The expectation value remains zero. So, okay, that's a three-dimensional example, which very much impressed me at the time, with the late Daniel Amit from that point of view. But the question to which I haven't found an answer since is, are there D = 4 non-supersymmetric systems which have flat quantum directions? All attempts up to now to find the no-go theorem have failed. On the other hand, I'm not familiar with an example. And I would be very happy if one could, by various index theorem or other attempts, to be able to either get rid of this idea that there could be non-supersymmetric theories with finite non-supersymmetric systems with flat quantum directions. If they were there, I think they would play a role in physics, but maybe it's just impossible to have them. And as I said in the beginning, I'm ignoring for now, I'm setting aside the case how to obtain in such a context a very small non-zero cosmological constant. Okay, so after discussing the two phases of the system, let's go back to other phases, and these are the phases of gate theory, gravity, and strings theory. A very simplistic but powerful method which was developed over the years is the following. First, you identify in the system what are the most important players. You estimate the free energy or the entropy of the players if you can identify who they are, and then see who is going to dominate for each range of parameters. This can give you a very good idea, it has given over the decades a very good idea on what are the possible phases of the system. So for example, if you look at gate theories, when I can identify the players as diodes. So consider a lattice where the x-axis n gives you the unit, how many electric charges does the elementary player have, and m is how many units of magnetic charge the player has. You look at these objects, you estimate their free energy as a function of the temperature, so you know the energy of the object, and you know their entropy, so you can write down the free energy. Whenever the free energy seems to be negative, this could be a phase. Those configurations which produce a negative free energy can be the dominant players in that phase. So in general, the function of the temperature n and m, this is the type of function that you get. T is the temperature, so you get, because of the various dualities in these systems, n squared times t plus m squared over t. If this, for example, is a Zn lattice gate theory, then there is another parameter n. And whenever, for a given temperature, you have n and m's such that this combination on the left-hand side is smaller than some number over 1 over n, then all operators which sit inside there are candidates to condense. And then they compete among themselves. And for example, in the case here, this depends on the details, which of them would win. But if the guy who wins is some non-zero object along this axis, then for low energy you would get the Brout and Higgs phenomenon. On the other hand, if you go to high energies, then you will see that the ellipse, which contains the operators which may condense, actually is vertical. And in that case, the operators which condense are magnetic, and you get the Brout and Higgs dual, which is a magnetic dual of that phenomena, which is confinement. If you would be in a situation, which I haven't drawn here, where the circle would only cover the origin, the ellipse would only cover the origin, in that situation what would have been in the Coulomb phase. Now, I should say that in this analysis, I think one really understood what was the dynamics which had driven gate theories. Namely, you could have a Coulomb phase, you could have a confinement phase, a dual Brout and Higgs phase, and the Brout and Higgs phase. However, what was not appreciated enough in this analysis was trying to obtain the conformal phases, Banks and Sachs, or what was identified by Seiber in theories which have some supersymmetry of various degrees. Now, one can also ask what happens in the presence of a theta parameter. Again, in this case, dions, particles which have magnetic charges will anyhow become dions. And as was suggested by 't Hooft and shown by Cardi and myself that it can be realized, one can also get, for certain ellipses, oblique confinement. So this is a situation where really, except the conformal phases, by identifying the players of the system, one really understood what are the possible phases. Then this had to be corroborated by more rigorous results, but more rigorous results up to now required higher degrees of symmetry. And indeed, for the case of like n=2 supersymmetric series, by the work of Seiberg and Witten, this has made further more rigorous justification in other circumstances. What about gravity? So in gravity, what are the players? So let me take a simple case, which is ADS5 case. In that case, the players are graviton radiation, other single trace operators. There are strings, there are Schwarzschild black holes, and there are black holes in ADS. Then you can do the same game. Here, let me emphasize the entropy. And if you look at the table on the left-hand side, you see that the theory, you can identify that the theory goes through various phases as a function of energy here, not a parameter T. I'm just identifying here who are the relevant players for a certain set of energies. So on the left-hand side, you see first the typical radiation in 10 dimensions, so the entropy is e⁻⁻⁻. Then you see the Hagedorn behavior. Then you see the Schwarzschild black holes with their negative specific heat. And then you see on the asymptotic part, the amazing result of Gibbons and Hawking that black holes actually give positive specific heat in ADS and give a result of e⁻⁴. So this is a microcanonical ensemble. If one is looking for a phase transition, let's translate that to a temperature, to a canonical ensemble. In that case, you see on the right-hand side, first the positive specific heat of a 10-dimensional theory, then without entering into the fine structure, the Hagedorn part. Then you see the negative specific heat of Schwarzschild black holes, and at the end you see the positive specific heat of black holes in ADS. This picture invites a Maxwell construction, which you see by the solid bold black line, and you see inside this gravitational system a first order phase transition. So a phase transition between a situation where you have thermal radiation and then where you have ADS. This phase transition, by the way, changes topology, because thermal radiation has a pi1 which is non-zero. while the black hole has a 0 pi 1. So this is a phase transition in which also topology has been changed. Okay, now you can add more players, and as you get more players, you're going to have more phases. You can have black brains, you can have young Mill theories, depends on what in more dimensions you are. All of these are very simplistic arguments, and my hope is that more rigorous a la Seibert-Witten calculations eventually will validate, and maybe we'll also realize, like in the case of conformal symmetries, that we missed some interesting phases. And here, let me end by the new results. A little bit, let's discuss phase transition in string theory. So consider some various ADS3 cross N models, which have a parameter K. The algebraic parameter on the worksheet is the level K of SL2R, which is, in bulk language, measures how curved you are in string scale. So it's the radius of curvature of ADS relative to the string scale. And with work with Givon, Kutasov, and Amit Server, we have shown that if you look at the entropy of the system for various energies in various levels of K, I've written here just reminding you that C effective is not exactly C, but it's C minus 24 times the vacuum energy in the conformal theory. It's important here. Then you can look what happens at high energy, and what you find at high energy is a phase transition at the level of Q equal 1, which is very stringy. You find that on the one hand, on the right-hand side, the entropy is dominated by BTZ black holes, while on the left-hand side, it is dominated by long strings, which Ogurim and Maldacena have uncovered in their analysis of ADS3 cross N. Now, this is because this is the behavior of the entropy at high energy. There is this transition. The entropies match exactly, and there are many other arguments why something happens there. But this is the UV manifestation of the transition. Any transition should also have an IR manifestation. And indeed, the IR manifestation, from our point of view, was found in the work of Gabriel Kupakumar and Hall, when they found that, there are, at the point K equal 1, a discrete infinity of trajectories which have massless particles which include all possible spins. Now, they somehow discuss a little more that this is this dreamland where the tension vanishes, and indeed some tension vanishes in that theory, but on the other hand, there are most of the excitations have tension. So I would say more this is an island. This point K equal 1 is an island on the way to obtain a theory with alpha, where the expectation value of alpha prime is a parameter. And in this case, one actually, and this with work which we are now doing with Gerbert, Kleban, Hall, and Porati, we are trying to learn much more about this K equal 1 equals theory, which is I think an island on the way of having a theory of no scale. Now notice, if we connect this to the beginning of the talk, that this looks at least like a new type of a phase transition, because these particles, when you move away from K equal 1, which is a subtle issue, how to move in one direction there, you find out that either these are particles which obey the Brout and Higgs mechanism, or they are Goldstone bosons. But in any case, there are not a finite number of them, there are an infinite number of them. So this is somehow a phenomenon which is stringy in a way, that it's much more strong than what happens in just, or the consequences are much more dramatic than the consequences in the Brout and Higgs mechanism and the Goldstone transition. With this, I finish my 3 stories, and thank you very much. Toda rabah.